Okay, so the first thing is lab exam 3 is this week in lab. This is the last lab exam. And so it just covers all the stuff from all the labs that we've done. If you can't make it to your lab this week, but you can make it to another lab, that's always fine. So you're going to do the lab exam, which never take very long. And then I'm going to give you, if you remember taking right at the beginning that bubble sheet test on sort of intuition about physics, it doesn't count for your grade. It's just for us. But so after you do the lab exam, you're going to do the 30-ish minute, real quick post-test for that. Just so we can check and see how your intuition is coming along, keep working on how to improve that kind of thing. But it doesn't go in your grade. Okay. The lab exam, though, that does go in your grade. Okay. Any questions about the lab exam? And then the regular exam 3 is a week from Wednesday. And I still have to think about what I'm going to put on that exam. We might do like rotational kinematics, but not kinetics, something like that. But I'll tell you more about that on Wednesday. And then, other than that, it's just getting in the weekly assignment that you already have, and the final. So it's getting to the end. Any questions about the end of the semester? Yes?
What is our final? Is it going to be like a lab exam?
No lab stuff, just like the other exams, maybe a touch longer, but not much longer. Yes?
When is the final?
I can look right now, I think. Okay, so we meet Mondays at noon. Mondays at noon. So it'll be the first day of finals week, Monday, the 11th from 2 to really 4. It's not going to be 3 hours, just 2 hours. And even that is going to be more time than you need. Yep.
On the other side, because we meet Monday, Wednesday?
There's what?
On the other side, because we meet Monday, Wednesday?
Ooh. Monday, Wednesday. What the heck? What does that mean? 11 to 2. Okay, well, it's going to be on Monday, either at 11 or at 2. I better get to the bottom of that. Thank you. So I guess that is, I have no idea what that stuff means. It used to be so much simpler. Monday, Wednesday, Friday. Okay, yeah. I think you're right. I did not see that, but it looks like it's going to be Monday at 11, but I'll make sure about that. Any other questions about the end of the semester? Okay. One thing about grades, I currently just have the grades, like on D2L, if you go look at your grades, I'm not taking out any of the stuff that the syllabus says that it takes out. I am going to do that. And so when I do, like your grades that are listed are going to get a little bump, you know? So like, for example, your lowest weekly assignment is going to be dropped from your grade. If you look at your overall grade in D2L right now, it doesn't look like it is. Okay, so there's some stuff coming up that'll give your grade a little bit of a boost. So I'm going to drop one weekly assignment. It doesn't currently show up that way. I'm going to drop 2 quizzes. It currently doesn't show up that way. We need to have one more quiz, which I think I'm just going to do with the final. So it'll drop your 2 lowest quiz scores, and then your quiz score will be just your highest 2 quizzes. And then the last thing is, remember, your exam 4 score, if it's higher than any of your first 3 exam scores, it'll replace the lowest one of those. It'll replace one of those. So if you have one test that you got 30% on or something, once you take exam 4, say you get 80% on that, your score will change to being 80% on your final and 80% on your exam that it was a 30 before. So there's a bunch of stuff coming up that'll give just little boosts to your score. So just so you know, I just haven't made those adjustments yet because I kind of wanted to show everything for now, but all right, that's all. Before I get into new material, does anyone want me to go over any homework problems? I know you did all those rotational kinematics problems. Did those all make okay sense? Okay. So now we're getting into rotational kinetics. And remember, what kinetics is when you combine kinematics with the causes of motion. So now we're adding the causes of rotational motion. The big equation in rotational kinetics is, I think the best way to think of it is just rotational Newton's second law. It looks like Newton's second law in just about every way. It just deals with rotations, not linear motion, not translational motion. And what it says is MA net is equal to the moment of inertia of the body around the point A times the angular acceleration of the body. So MA net is the sum of all the moments around the point A. I is the mass moment of inertia. I'll just call it the moment of inertia. About the point A. And this is the angular acceleration that we defined last week. And you can think of it very much like Newton's second law. Moments are like they're sort of the rotational version of a force. The moment of inertia is the rotational version of the mass. It tells you how easy or hard it is to get a thing rotating. And then the angular acceleration is like a rotational version of the acceleration. So that'll sort of help you remember this stuff, remember the meaning of this stuff. But before we can talk about this equation, you already know what angular acceleration is, but I have to define the moment of inertia, and I have to define the moment or the torque. Okay? So first I'm going to define the moment of inertia, and this is more trivia than anything, but it's really the mass moment of inertia. There are other types of moment of inertia, but I'll just call it moment of inertia because this is the only one we're dealing with in this class. And this is a positive scalar. A scalar means it's not a vector. That's large if an object is hard to rotate, and small if an object is easy to rotate. The subscript, okay, so we're going to denote it capital I with a subscript. And the subscript denotes the point that the object is rotating about. Okay, so you can think of that like in this class, that's always going to be a hinge or a pin, something that the object can spin around, but at that point it's stuck to the ground or it's the wall or whatever, you know. So what does it mean for, like, this is something you can calculate. What is it that makes the moment of inertia large or small? This is the meaning of it, and I'm not going to give you like a mathematical definition, but a high moment of inertia, a high I sub A, is if mass is distributed far from that about point, that point A. And a low moment of inertia is if the mass is pulled more tightly to the about point A. So even if you have the same object, it has the same mass. If all of its mass is spread way far out away from the hinge that it's rotating around, it's hard to get it rotating. It takes more effort to start it rotating. If all of its mass is pulled in tight to the hinge, it's easier to get it rotating. You've seen this in like Olympic type sports are really good examples of this. You see it in a few different cases really clearly. So here's what it means intuitively. In gymnastics or diving, there are, multiple ways you can do flips, and so like, let's think of in gymnastics, like in the Olympics, someone does a double backflip. These are two different ways that they'll do it. One is their body will be in a position like this. Okay, they're rotating around like this. And another one is their body will be in a position like this. Now you get a lot more difficulty points for doing your double backflip with your body straight like this. And the reason for that is, say this is the same person, so it's the same mass and everything. This person on the left, if you think of the point that they're rotating around is their center of mass. So let's say it's right there, and let's say on this person, their center of mass is right here. Okay? On the left, they're, as much as they can, pulling all their mass right in close to the about point. Okay? They're doing everything they can to make the moment of inertia small. In this case, I mean, they could raise their hands over their head, but other than that, like, they're pretty much as far spread out from the center of mass as they can be. That means that in this case, this is easy to rotate. And on the right, this is hard to rotate. So what that means for difficulty is if you're going to do a double flip with your body in this stretched out position on the right, you have to get a lot higher in the air because you're not going to be able to rotate as fast. Okay? On the other hand, if you put your body in this tuck position, you can do a double backflip without getting as much height. You don't need as much power because you can spin really quickly. The units for moment of inertia are always units of mass times units of length squared. So we're going to be doing this all in SI units. And that means that the SI units for moment of inertia are kilogram meters squared. In order to calculate the moment of inertia, to give you the definition of it, it takes integral calculus. And so I'm not going into that, but I will give you the way to do this, some formulas to use for rectangular shapes. So here are the moments of inertia. For a rectangle. Rotating about various points. And when I say rotating about various points, what I mean is that's the location of the hinge or the pin. Okay, so let's say we have a rectangle with a height of W and a length of L, and a mass of lowercase m. So first, let's think about if the hinge is right at the center. Okay. What's the mass moment of inertia for this rectangle with the hinge right at the center? I sub A is equal to 1/12 times the mass times the quantity length squared plus width squared. Next, let's do, so now what I'm doing is I'm locating the hinge at the end of the long side, and these two are both exactly the same mathematically, all the way in the long direction, but in the middle of the short direction. Okay, so putting a hinge here or a hinge here. How hard is it to get this thing rotating? Are you with me on what I'm talking about? No? Okay, great. So this is 1/3 times the mass times the length squared plus 1/12 times the mass times the width squared. These all come from sort of complicated integrals, and so you're just gonna, I'll give you these formulas on tests and everything, but you just have to know how to use these formulas. Okay, next, at either of these 2 points C, so if you put a hinge all the way to the end of the short side, but in the middle of the long side, then that is 1/3 mass times the width squared plus 1/12 mass times the length squared. So it just changes which one has the third and which one has the 12th. And then the last one, in any of the corners, so these are D. So if you put a hinge at any one of those corners, how hard is it to get this thing rotating? And that is 1/3 times the mass times the quantity length squared plus width squared. Question?
What if it isn't like a rectangle?
Yeah, there's other formulas for different things, but all the problems you're going to do involve.
With hinges and stuff, they're going to be they're going to be rectangles.
Yeah, everything's going to be a rectangle that you're going to do calculations for, but you can do the same. They're the same thing for circles and triangles and everything. You just won't need them. Okay, well, if it's harder to rotate something when its mass is spread out far from the hinge, and it's easier to rotate something if the mass is close to the hinge, which of these would you expect to be the smallest? So C is the second smallest. The smallest is A. It's just right it's as much in the middle of stuff as you can be, So what I have here, this is the smallest. And the hardest to get something rotating is when the hinge is at the corner. That's as much as stuff can be spread out from the hinge. And so this is the largest of those values. And then B and C are somewhere in between those two. One thing I want you to notice because of the squares, like notice length and width are squared in all of these. If one dimension is way smaller than the other, let's say if one dimension is smaller than the other, you can often treat the small dimension as 0. In calculating the moment of inertia. Okay, so how does that work? Well, let's say, so let me just give you an example. Let's say that we have a rectangle that has a length of 5 meters and a thickness of 0.5 meter. Okay. And let's say that, I don't know, the mass is 10 kilograms. And let's say we want to calculate the moment of inertia around the center. Okay. Well, the formula says 1/12 times the mass times the length squared plus the width squared and so that comes out to be 0.83 repeating times 5 squared is 25. 0.5 squared is 0.25. Can you punch that in for me? Bless you. 20.96 kilogram meters squared. What if we had assumed that the thickness was 0? So if we had chosen the width to be equal to 0, we would have gotten 1/12 times 10 times 5 squared plus 0 squared, which is 250 twelfths. What's that? .8 repeating?
No, 3 repeating.
Oh. So you can see, even though 0.5 isn't really that much smaller than 5, the moments of inertia are very, very close. Okay? So, and the reason for that is the differences between those, you're squaring those differences. So something, in this case, these are, the 0.5 is 1/10 of the 5. Well, if you square 1/10, you get 1/100th. And so if those dimensions are different by a factor of 10, the moments of inertia are different by a factor of 100. Okay, and so what that means is sometimes you'll see problems where it doesn't even give the second dimension. In that case, just assume that it's 0. Just assume that it's pretty small compared to the other one, and so it's not going to have a big effect on the moment of inertia. So if you're ever not given a dimension, just assume that it's small. And treat it as 0. Okay, the next thing that we have to be able to calculate, and the last thing, is the moment, or the torque. Physicists tend to call moments and torques the same thing. For engineers, torques tend to mean a very specific combination of moments, and so that's just sort of like a practical difference in the way people talk about it. But in this class, you can talk about a torque or a moment as being the same thing. And so, like, let's say you have this object, and the hinge for the object is here. And let's say that a force acts at some distance away from the hinge, and the force that acts is perpendicular to the distance, perpendicular to that line between the axis and where the force acts. Okay, so I'll call this P, that's where the force acts. This is the force F. And the distance between A and P, I'm going to call D. That's that distance. If the force F is perpendicular to the line between A and P, then the moment about A is equal to plus or minus force times distance D. Okay, how do you know whether it's plus or minus? If that force would tend to make it rotate counterclockwise around the hinge, then it's positive. Just like before when we were talking about rotational kinematics, counterclockwise is positive. And clockwise is negative. Okay, so let's do an example. Let's say you have a rectangle like this, and let's say that it has a length of 1 meter and a height of 0.2 meters. And let's say that the hinge is here. And let's say that the force is straight down here with a magnitude of 50 newtons. What's the moment produced by this 50 Newton force? Okay, well, first you have to check whether, so if this is the point P, where that force is applied, the first thing you have to check is that that force is perpendicular to the line between A and P. So here's the line between A and P. Is the force perpendicular to that dotted line? Yeah, so that's good. So we can use this formula. Now the moment then is equal to plus or minus the force of 50 times the distance. What's the distance between A and P? 0.5 meters, yep. And now the last thing you have to do is think, if this force is the only thing being applied, is it going to make this object rotate clockwise or counterclockwise around that hinge? Counterclockwise, and so we want the positive. And so this moment is positive 25. I haven't said what the units are yet, but you can actually see it from the calculation because we have units of force times units of length, and so this is Newton meters. Notice that, if you changed where the hinge is, that same force could produce all sorts of different moments. And in a lot of cases, it could go from positive to negative and stuff like that, okay? So where that hinge is has a big effect on the moment. So what is a moment intuitively? Well, a moment is a thing that gets something rotating. I think the easiest way to think of it is like a big wrench turning a bolt. So say you have this bolt that's hard to turn, and you're trying to turn it with this wrench. And say that you're capable of, you know that you can apply 100 newtons of force to this wrench. So where do you want to apply that force if you want to effectively turn this bolt? Let's think of 3 possible locations. So first, let's think like right here. Second, let's think right here. And third, let's think right here. It's the same force in all 3 cases, but probably from experience, if you try to turn a wrench by applying a force right where the bolt is, it's not going to ever turn. You could apply 1,000,000 newtons and you'd rip the bolt right out of the wall, but it would never turn, okay? That's because in that calculation of the moment, that value of D is 0 there, okay? And so the moment that you get is 0, even if the force is big. In the second case, where it's in the middle, now you're going to get something to happen, But if you are having a really hard time turning this bolt, you know also from experience, you're going to get the best result by applying all the force you can apply all the way at the end, okay? And that's because you have that 100 newtons of force multiplied by the biggest value of D. Okay, so that's what a moment is. This combination of the force and where that force is located determines how effectively you're going to cause something to rotate. So this one won't make it turn. This one out here will make it turn the most easily. Okay, the units for moments. Is always units of force times units of length. And so the SI units for moment are going to be Newton meters. One thing that's interesting about this is Newton meters is, if you remember the definition of joules that we used for energy, Newton meters really is a joule. But we're not going to use the term joule for anything except energy, even though those units do match, okay? So this is a joule, but don't call it that. That's just to avoid getting confused about whether we're doing energy or rotational calculations. Okay, so here's the last thing about moments. What if where the force is applied and where the hinge is, the line between P and A just isn't perpendicular to the force? You know, it's easy to imagine a case like that. So what if the force isn't perpendicular to the line from A to P? So here's an example of that. Let's say this is the body. And let's say this is the hinge. And this is the point where the force is applied, and the force vector is like this. Well, draw the line from A to P, and it's easy to see that it's not perpendicular to that force vector. Okay? Well, in order to figure out how to deal with this, you have to understand the idea of a line of action. So the line of action of a force is a line that's parallel to the force and the line goes through where the force is applied. So this is the line of action of the force. Anybody have any questions about what I mean by that? You can think of it as like the line that force vector lives in. Okay? Well, once you've identified that line of action, you can always move the force anywhere along its line of action without changing the behavior. This isn't something physically that you do, it's a mathematical sort of trick, you know. Just imagine that that force is somewhere else along its line of action. So let's say without changing the problem. So then in this case, all you have to do is move the force along its line of action until you get to the spot where the line from the force to A is perpendicular to the force vector. And then you can use the rule that we talked about before. Any questions about that? Okay, well, let's do a couple example problems. So let's say we have a rectangle. Let's say the height is 3 meters. The width is 1 meter. There's a force of 10 newtons applied there, and a force of 20 newtons applied here. And then let's think of a point at the center and a point at this corner. And the question we want to answer is, what's the net moment? That's the sum of all the moments. If the hinge is first at the point A in the center, and second at the point B in the corner. Okay? So for the first one, for part A, we have a 20 Newton force there and a 10 Newton force here. And our hinge is right at the center. Well, the first thing I'm going to do is just draw the lines of action of these two. So the 20 Newton force has a line of action like this. And the 10 Newton force has a line of action like this. And to calculate each one of these moments, we're going to move these forces along their line of action so that the line between the force and the hinge is perpendicular to the force. Are you with me on that? So we're going to move the 20 Newton force along its line of action to here. We're going to move the 10 Newton force along its line of action to here. Anybody have any questions about that? And so the net moment is, first I'll do the one for the 20 Newton force. That's plus or minus. The force is 20. What's the distance from this relocated 20 Newton force to A? Yep, 0.5. And if that was the only force acting, would it make this thing rotate clockwise or counterclockwise? Counter, that's right. So this is positive. Okay, and then we'll go to the second one. So plus or minus 10 newtons. What's the distance from this relocated force to A?
And that one be 0.5 and the other one be 1.5.
This is, for the 10 Newton force, this is the distance that we're talking about. And so this one would be 1.5. It's always that perpendicular distance that you want. Because remember, you know, like if you think of that wrench again, you know, how well would it work if I tried to apply 100 Newton force straight along it? It wouldn't turn it at all. And that's because the force and that distance are in the same direction. They have to be perpendicular. Okay, and would that 10 Newton force make it rotate clockwise or counterclockwise? Counterclockwise again. So imagine just taking a hammer and giving a little tap there, it would rotate like this.
Yeah.
Okay, so this comes out to be 10 plus 15, so 25 Newton meters. And positive says that if those are the only forces acting on this, it's going to make it rotate counterclockwise. And now let's go to part B. So this time, the hinge is going to be up in the top left corner. We have the 20 Newton force there. We have the 10 Newton force here. The hinge is here. So for each one of these, again, let's think about the line of action. Here's the line of action of the 20 Newton force. Here's the line of action of the 10 Newton force. The 10 Newton force, we don't have to move at all. It's already perpendicular to the line from the hinge to the force. Do you see that? The 20 Newton force, oh, well, we don't have to move that one either. That force is already perpendicular to the line from B to where it's applied. And so MA net is equal to, so the 20 Newton force, what's the distance from the 20 Newton to the hinge? 1, yep. And would that make it rotate clockwise or counterclockwise? counter, so this is positive. And then we have plus or minus 10 newtons. What's the distance from the 10 Newton to that hinge? 3, yep, exactly. And clockwise or counterclockwise? Counter. These have all been counterclockwise. That's boring. So 30 plus 20. So this time you get 50 Newton meters. Okay, so now we're going to use this idea with rotational Newton's second law. So A is always going to be some kind of pivot point, like a hinge. Whenever there's weight in a problem, you're always going to apply the weight at the center of the object. That's important. So mg always acts at the center of the body. It's really the center of mass of the body. And the last thing we're going to use is that the hinge itself applies forces we don't know. It applies an x component and a y component. Of forces. But since they're acting at the hinge, there's no distance, there's no d in the calculation, so they produce zero moment. Okay, so let's just do a problem. Let's say that you have a board that's connected to the wall by a hinge. And let's say that the length of the board is 2 meters. And the thickness is 0.1 meter. And the mass of the board is 10 kilograms. And I'm picturing this being on like a wall, so gravity is acting down towards the bottom of the page. So this way is down. So what's the angular acceleration of the board? Let's start by coming up with the moment of inertia of the board. So the moment of inertia with the hinge over there on the left, that's all the way at the extreme of the long side and in the middle of the short side. So this is going to use the formula 1/3 times the mass times the length squared plus 1/12 times the mass times the thickness squared. And so that comes out to be this one is 13.3 repeating. This one comes out to be 0.0083 repeating. Like, look at how tiny that part is, and that's because that thickness is small compared to the length. And so we get a value of 13.34 kilogram meter squared. So that's the mass moment of inertia. Now I'm going to draw a free body diagram. And what forces are there? There's a weight force that acts right at the middle, at the center of mass. So that's the mass times 9.81, so 98.1. And then at the hinge, there are these two unknown forces. I'll just call them Rx and Ry. But of course, like always, these are going to produce no moment. Because they're acting at the hinge. So the D in that calculation would be 0. Okay? And so what's the moment produced by the weight? That's going to be plus or minus a force of 98.1. What's the distance from that force to the hinge? 1 meter, yep. And would that downward force make it rotate clockwise or counterclockwise around the hinge? Clockwise, yep. So negative in this case. So the moment produced by the weight is negative 98.1. What's the moment produced by the forces at the hinge? Those are always 0 because the D value is always 0. And so now we can put this all together, you know, MA net, the net moment around that hinge, is negative 98.1 plus 0, so negative 98.1. And then the rotational Newton's second law, I always just call that Rn2L, is negative 98.1, that's the total moment, is equal to the moment of inertia, 13.34, times the angular acceleration. And so the angular acceleration can someone divide 98.1 by 13.34? 0.35? Yeah. Negative 7.35 radians per second squared. Anybody have any questions about that? That's sort of a lot for one day. I'll stop there, but what we've really done, just like a reminder, is we learned how to apply these formulas for the moment of inertia for a rectangle, depending on where the hinge is. And then we learned how to move these forces along their line of action to calculate those moments. Okay, that's all.